Welcome to Knifer Middle School, 6th grade science, force and motion. Today we're going to look at goal 7. Students will explain and apply Newton's third law. Newton's third law reminds you that forces come in pairs. You can see a nice little picture of that because there are two pairs that are together. You know, like the fruit pairs. And get it? It's a joke. Nothing? Anyway. Newton's third law states that if one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first object. To sum that up, for every action, there is an equal and opposite reaction. For example, when you jump, you push on the ground also pushes back on you. When you paddle, you push the water pushes back on the paddle. And the gymnast push onto the vault also pushes up onto the gymnast. Now imagine if you had two people on roller skate and one person, the person in purple right over here, this person pushes. Do you think this person's going to move? You better believe it. That person's going to move and the person in purple is going to move as well. Equal and opposite. NASA needs to know this information because they study rocket engine thrust. They need to know that the flow pushed backward will cause that rocket to go up into the air. For every action, there's an equal and opposite reaction. Let's check out a little video.
We're here at Purdue University to talk about for every force, there's usually an equal and opposite force pushing the other way. So, for instance, if I push against this wall with my feet,
nice shoes.
The wall pushes back on me, and I can use that to shoot myself down the hallway. We don't even need a wall to push against. I can push against this medicine ball and throw it that way, and it'll push back at me, and I'll go that way. And this is a lot like how a jet engine works. It actually grabs air and throws it backwards, and that would push an airplane forward. So if I throw this hard enough, I should go backwards. But it's pretty tricky. And I'm traveling backwards at the speed of almost nothing. This doesn't just work with heavy things. We can take lots and lots of light things and throw them really fast, and they should push back on me as I push forward on them, and I should still fly backwards. Unfortunately, the question becomes, can I throw them fast enough, or basically push on them hard enough to make myself go backwards? And they're pretty light, so maybe not. But let's give it a try. Here we go. Ready? Yes.
He cheated.
We can now throw even smaller things. We've got a tank of carbon dioxide gas.
Oh, baby.
And if we let it out, it's speeding out that way. And so it has to be it's being pushed out that way. And so since it's pushed out that way, there has to be a force pushing back on us in order to throw it. And so if I throw basically lots and lots of tiny molecules of carbon dioxide, I can go backwards really fast like a jet engine. I just have to throw them faster. Here we go. 3, 2, 1.
Wow. I want to do that.
And we're gone. The end.
Love that. That's cool. So what opposes gravity? We all know that gravity is a force that pulls down on us, that causes us to have some form of weight. Well, actually, there's a force that pushes up against us called the normal. Okay, this force is from the ground or object pushing back up on some sort of object. For example, this backpack here on the table, the reason why it doesn't break the table and go right on through is because the table is applying an equal and opposite force up onto that backpack. Now, you might be thinking back of balanced and unbalanced forces and how those worked, but it's a little different. Action and reaction forces may or may not actually be equal. Action-reaction pairs are not always balanced. We've seen balanced forces before, for example, 20 newtons in both directions acting on this book. Well, if they're acting on that book, then that book won't move or change direction or do anything. Are action and reaction pairs considered to be balanced forces? The answer, absolutely not. Action-reaction forces do not cancel out because they are acting on different objects, not the same object. If I click back here, you see this purple and yellow arrows are both acting on this book. Let's take a look at this example. Let's take a look at the volleyball players. Over here on the left, this lady is spiking this volleyball. That means that she is applying a force on the volleyball as the volleyball is applying a force onto her arm. If we're looking in this case, it's a little different because both of these volleyball players are both acting on this one volleyball. That means that this would be considered a balanced force. This would be still considered an unbalanced force. Let's check out another video about Newton's third law.
It says simply when one body acts on another, then the second body acts back on the first with an equal and opposite force. So, simple example. I'm leaning on the desk. Why aren't I falling over? What's stopping me falling over? The desk. So, as I push on the desk is pushing on me. There's an equal and opposite force. I'm pushing on the desk is pushing on me, and it's stopping me fall over. Now, slightly variant on the same thing. I'm going to push on the desk. I push on the desk, and off I go. Why did I accelerate? Why did I accelerate? So the response, or the acceleration, comes from the Newton's third law paired. I'm pushing on the desk pushes on me, and that's why I moved away. Okay. Why did the balloon accelerate? There's a force involved. It accelerated, right? That means there's a force on the balloon. Where did the force come from? There's a Newton's third law thing going down here. Here's the balloon. Doesn't matter what's outside, it's full of air. But because of the pressure of the balloon, the elastic force of the air, the balloon pushes air out. That's one force in this process. There is a Newton's third law of force that acts in the other way. The air that's being expelled pushes on the balloon, which means the balloon accelerates. So it's the act of throwing stuff out the back, pushing stuff out, that causes the stuff that's pushed out, the Newton's third law, other force, pushes back on the balloon and accelerates it. What I've got here is a simple plastic bottle, but if you look on the outside, there's a couple of vents that are angled backwards. If you have a look closer, you can see the vents. I'm going to fill it with liquid nitrogen and boil it. So, liquid nitrogen.
We really need some liquid nitrogen. That would be cool.
One of the neat things about being a physicist is you get to play with some really fun toys. This is liquid nitrogen, which is one of the more fun ones. It's about a couple of hundred degrees below zero.
Ooh,
now,
cold.
So what I've got is I've got a boiling liquid. Here I did this with steam. I'm going to put liquid nitrogen, and I'm going to warm up the liquid nitrogen by putting in, this is just ordinary water. And we get this wonderful little jet engine.
Oh, neat.
So what's happening? There's high pressure in here. The pressure forces, warm it up again. The pressure inside forces the gas out, and the Newton's third law reaction force pushes the cylinder in the opposite direction, causing it to spin. There's a force of this plastic bottle on the gas going out, and there's a Newton's law force of the gas on the bottle spinning it in the other direction. And I have a jet engine here. Now, this is not an ordinary fire extinguisher. Every single reduction valve has been removed from this thing, so it's a fairly lethal fire extinguisher.
Yes.
When I crack the valve, it will empty itself in about 10 seconds. And I'm going to sit on the skateboard, hold on to this thing, crack the valve, and hopefully I will hurtle along behind the building. There's a huge force of the cylinder on the gas. And then that gas pushes back on the cylinder and on me, accelerating me. So, 4, 3, 2, 1.
Okay, that's sweet. I'm just saying, that is pretty sweet. I'm not going to lie. It's pretty cool. Love that. So, that was goal 7. Students will explain and apply Newton's third law. For every action, there's an equal and opposite reaction.
Let me put a little bit of water
That's good.